Hello, this video is about implementing monotonic reads session guarantee, and it will be based on the article present on the screen. My name is Ivan Fedyanin, I am software architect, and on this channel I am doing series of videos about distributed systems. We will start with short recap of the definition of monotonic reads. To see more detailed information about them, see my separate video about all client-centric consistency models. On this picture we have distributed storage system which consists of 3 servers. There is some replication happens between those servers, but we don't really care which type of replication, so let's assume that it's just eventually consistent. It means that writes made on one server will eventually be distributed across all servers. First, assume that each server has some writes, which were already done into the system. Next, client starts a session, depicted here with a red circle. And in scope of that session, he makes first read and then second read. Basically, monotonic reads session guarantee requires that all reads which client has seen during first read will also be visible during the second read. Or in other words, client should always see non-decreasing set of writes when he makes reads in scope of one session. Note that R3 made out of the session doesn't have the same requirement and it actually could see less writes. The simplest implementation could be just to use storage system in the non-distributed way. Client could always connect to the same replica, and it's obvious that in that case there will be no anomalies related to reads of that client from the same replica, because this replica will always have increasing set of writes. And sometimes it's okay to use such a method and lose benefits of distributed systems for achieving session guarantee of monotonic reads, but at other times it's not acceptable. What do you think would happen if one server goes down and client was using this server specifically? If client fails over to another server to make the rest of the reads, at this point session guarantee might be lost. Despite the drawback of this method, it's sometimes used in the industry because of its simplicity. For example, Shopify has shown in their engineering blog that they use such method and it works for them. They use MySQL database and proxy SQL cluster, and this cluster is responsible for keeping sessions sticky, so it's routing reads from one session always to one replica. More details can be found in their website. So let's try to solve this problem by making a system which literally ensures the correctness of the definition of monotonic reads. In a nutshell, the definition says that client during reads must always see the writes which it already read. So basically we just need to track which writes client has already read. For this we will assign to each write unique identifier with, and this with will be unique across all servers. Next, let's make several requirements to the servers. First, it's obvious that the servers must keep the actual data, which are shown here as green cells. Apart from that, servers must keep IDs of all the writes they have, and they are marked on this picture in red. Apart from that, each server has to keep for each data item in its database also IDs of all relevant writes to this specific data item. And the server must provide 2 interfaces. First, on each read request, it must return all relevant writes which are relevant to this specific variable which is being read. And second one, it has to provide an interface to tell whether specific set of writes is present on that server. Those are all the requirements to the servers, and the rest of the algorithm will be driven by the session manager. Its component, it will be in the middle between client and server, and it will be proxying client calls, and it will be responsible for selecting the server which will satisfy the monotonic reads guarantee. After each read, Session Manager will receive all relevant writes to that read from the server and will store it into its read set. And before making that read, Session Manager will have to iterate through all servers until it finds a server which contains all the writes which are present in Session Manager's read set. Let's see how it works. We have client, Session Manager, and two servers. Servers have a location for the data itself. Also, they have write set, the place where IDs of all writes are stored, and relevant writes to each data item which is stored in its data location. Client wants to write x equals 1 and sends the request to the Session Manager. For the write, Session Manager it can choose any server without any specific checks before, so it randomly chooses server 1. And it just forwards the request to server 1, and in server 1, under the hood, there are several actions happen. So first, it writes this write into its data storage, it assigns identifier with 1 to this write, and adds it to its write set, and to storage of relevant writes to the variable x. It means that this write has a direct effect on the value of x. And then it just responds with the data to Session Manager, and Session Manager just forwards it back to client. Next, client wants to make second write, and it sends a write request x equals 2 to the Session Manager. Session Manager can randomly choose server, but for simplicity of our illustration and because they are not important to reading your writes guarantee, we will assume that server will always now will be choosing randomly server 1. So it sent this request to server 1. It does all the same stuff as it did before for previous write. The only interesting part is to notice that in the relevant write set, we have completely replaced with 1 with 2. Because it's just overrides the value, and the previous write it's not important because we already have a newer write. And then it responds back to client. And to really illustrate the concept of relevant writes, we need to make the third read to be an increment. It will just increment x by 1. So when Session Manager forwards this request to server 1, now it's assigned with 3. And this time, this with 3, it's not replaces previous with in relevant writes, but instead it is appended, because now it's relative, it's an increment, and for it to be meaningful, we need also to know previous value. And this can illustrate us that potentially this relevant write set could be very large, potentially infinite. To make the point about reading your writes, so we need to have a system in partially replicated state. So let's assume that there is a partial replication happened from server 1 to server 2, and only 2 first writes are replicated. So it means that server 2 is now behind by 1 write comparing to server 1. Now let's look how reads would work. Client issues a read, and now Session Manager's responsibility is to ensure that the monotonic reads guarantee is satisfied. But at the same time, this is the very first read in this session by this client. So there is nothing to satisfy, and the Session Manager can just choose any random server without any further checks. So it chooses server 2, and the server 2 together with the result of the read with the value of x, it returns a relevant write which led to this x value with 2. Session Manager stores this with 2 into its read set, and now during next reads, Session Manager has to ensure that whichever server it chooses, it contains this with 2 in its write set, just to satisfy monotonic reads guarantee. On the second read, Session Manager has to iterate through all servers and ensure that they contain with 2. It starts from server 1 and the server 1 responds affirmatively, so it makes the read from server 1, and now server 1 returns its current relevant writes for the variable x, which is with 2 and with 3. And session manager just adds those writes into its read set, so now its read set contains both with 2 and with 3. When clients wants to make another read, session manager has to find a server which has all writes which are present in client read set. It starts iterating from server 2. It finds that server 2 doesn't have all the writes because it's behind. So it asks the same question from server 1, and because server 1 responds positively, it makes the read from server 1 and returns the result to client. So we have just seen how session manager prevented non-monotonic read from lagging server. As you can see, this method works, but it has major drawbacks. First one, that servers and session manager has to keep huge sets of widths, and second one, that session manager has to send over the network its full potentially huge set of widths to servers, and it means that for real-world system it's not really practical, because such sets of widths, they will grow very large and it will not be possible to store them all and send them over the network. So this implementation, it's very good for illustration purposes because it's easy to understand and it matches with the definition, but it's not practical. In reality, monotonic reads are implemented with version vectors. The main idea that we are compacting all the widths stored on the server into a small vector, and this vector will contain a number of elements which are equal to the number of servers. Each server needs to have its own clock. Those could be any clock, for example, real-time clock, Lampert clock, or just counters. The only requirement to the clock is that their value should be bigger for any subsequent write than for previous writes. Each server will have a vector containing the clocks of all other servers, and each server will be directly responsible only for one item in this vector, for its own clock, depicted here with red for each server. And when replication between server happens, together with the data with writes, the clock values are also synchronized. Each write has an assigned write ID with, which consists of two components. First one is the server ID, which made the write, and the second one is just clock value of that server. Also, to make it work, we need to define two operations. First one is the dominance operation. So we say that vector v1 dominates vector v2 if we compare each elements of those vectors and all elements of v1 are larger or equal than each corresponding element of v2. It's needed to define which server is ahead and which is behind, so we can do it just by comparing the vectors of the two servers. Secondly, we need to define merge operation between two vectors. When two vectors are merged, we just need to select maximum clock value for each server correspondingly. It serves the purpose of updating version vectors on servers when replication happens, and also updating version vector on the session manager when it makes the reads. Now, when we know the basics, let's see how it works together. And now we will focus only on servers, just leaving out what happens on client. In the initial state, each servers have no writes, their clocks are zeros, and their version vectors are empty. And also we have some writes coming in the specific order to the servers. When first write x equals 1 comes to the first server, its clock are incremented, the version vector is updated, and the value of x is stored in its data area. Next, second write x equals 2 coming to the server, and again clock are incremented, version vector is updated, and write is stored. And the same happens with the third write, y equals 3. Next two writes are coming at server 2. They update that variable, they update version vector and the clock of the server. And the rest of the writes, they come to server 1 and the same happens. By this time, both servers has received different set of writes. And by looking at their version vectors, we could see that server 1 is behind of the server 2 and server 2 is behind server 1. Next, replication from server 1 to server 2 happens, and together with data replication, server 2 version vector is updated with the latest values from server 1. Now we can see that version vector of server 2 dominates the version vector of server 1, meaning that server 2 is ahead and server 1 is behind, it's lagging. And the same opposite replication happens, and now two servers are exactly at the same state, which can be seen by just comparing their version vectors. Now we don't have to store and compare each write to see that they are at the same state. We need just to compare small version vectors, and in this case, when we have only two servers, in this version vector we will have only two elements. Finally, to make the write, it's very simple, and Session Manager just connects to any available server and makes that write. Making read is a bit more complex. After each read, Session Manager has to receive a version vector from the server and merge it into its read vector. And next, before the reads, Session Manager has to find server which version vector dominates its read vector. Notice that here we don't need to track relevant writes. Instead, we just say that version vector received after the read, it approximately represents relevant writes made up to that point. It means basically that our condition for relevant writes is most strict, so we would require actually more writes to be present on the server than needed, but because of this we don't have to keep track of them, and it's a very good trade-off. Let's see an example how it works for writes. In the initial state, we don't have any writes yet, the system is completely empty, all variables are zeros or not present. So when client makes first write x equals 1, it's forwarded by Session Manager to any random server, server 2 in this case, and server 2 it increments its clock, updates version vectors, stores this write x equals 1 into its storage, and responds to Session Manager, which proxies this response back to the client. Next, client wants to make second write of variable x and override its value to 2, and the same process happens. It's sent to Session Manager sends it to random server, which is again server 2 in this case, and this server updates clocks version vectors, stores the latest value, responds to the client. Next, third write made by the client. It's now not an override of variable, but increment of variable, but the rest happens the same. It's sent to the Session Manager, it ends up in server 2, clock are incremented, version vectors are updated, and the result is returned back to client. Next, for the illustrative purposes, let's assume that partial replication happened and the first two writes are replicated from server 2 to server 1. And together with the writes, version vectors are also updated. So now by looking only at the version vectors, we can see that the server 1 is one write behind of the server 2. Now let's use this state in which we ended up as an initial state to illustrate how reads would work. Client makes first read, and now, because it's read, Session Manager has to ensure that monotonic reads guarantee is satisfied. But because this is the very first read, there is nothing to check. So it just sends it to the random server, which is server 1 in this case. And when server 1 responds, it also provides its current version vector. And now session manager, it stores its version vectors in its read vector and responds to client. When client makes the second read, session manager now needs to check that its read vector is dominated by the server version vector. So first it checks server 2, and this condition is satisfied because server 2 is ahead, and it makes the read from server 2, and in the response it gets this version vector together with the data item, and it merges this version vector to its read set and responds to client. Now client wants to make the third read. Session manager iterates through all servers to find the one which version vector dominates its read vector. It starts with server 1 and it detects that its version vector not dominates its read set because it's behind. So it switches to server 2, makes the same check and finds that server 2 is suitable for making the read. Thus, the read is made from server 2 and the result is returned to client. This algorithm could be even further optimized. First, session manager can try to connect always to the same server, and in that case it does not need to spend time to check all of those conditions about version vectors. If something bad happens with the server, then session manager can just make a failover to another server, and during that failover it will use version vectors and its read set to choose such a server for failover so that the guarantee still will hold and all reads will continue to be monotonic. And to even more speed up that failover, session manager could cache version vectors for all the servers, and thus failover could be faster. We have just seen how to effectively implement monotonic reads guarantee on top of eventually consistent data store. For this, we have introduced Session Manager, component which is responsible for keeping read vector, which contains clock values from all servers corresponding to reads made within the session. Additionally, each server has to keep only a small vector of clocks of all other servers, and the size of that vector will be equal to the number of the servers in the system. It's much more effective than straightforward implementation because we don't need to store and send huge sets of IDs. And also it solves the failover problem, which had this sticky session implementation. I also recommend my other video about client-centric consistency models with more thorough definitions, descriptions, examples of reading your writes, monotonic writes, and write follows read. Apart from that, I have a video on fundamentals of consistency, which introduces what is the consistency and covers some basic models such as linearizability, sequential consistency, FIFO consistency, and causal consistency. If you are interested in the implementation of other session guarantees, then just look at the other videos on my channel. So if you liked the video, please subscribe and then you'll get news about any new videos on this topic about distributed systems. Bye! Hope to see you again!